Hi there. So in this lecture, I've got some very ambitious goals. I'm going to need you to hang with me because sometimes the math isn't so easy to follow. So just remember that at any time, if you need to pause me in order to follow the math, please do so, okay? It's not like talking to me in person where I get really excited and talk too fast. So here we go. One of the goals of today, the first goal of today, is to show you what the differential form of the Ampere-Maxwell Law is. Now previously, in another lecture, which you should definitely watch if you haven't seen it yet, we derived the differential form of Ampere's law without the displacement current. Then in another lecture, which you should definitely watch, I showed you what the displacement current definition was and showed you the Ampere-Maxwell Law, the modified Ampere-Maxwell Law, with the displacement current in the integral form. And so now I'm going to take that and I'm going to show you the differential form of the Ampere-Maxwell Law. So first of all, how did we get the differential form of Ampere's law without the displacement current? Remember that we had the integral form of Ampere's law, which is that the integral about a closed loop of b dot ds is equal to mu naught times I enclosed. And I enclosed is the enclosed current, mu naught is 4 pi times 10 to the minus 7 in SI units, B is the magnetic field, and ds is the direction that you're walking around in your Amperian loop, okay? So remember that what we said for Amperian loops was, just imagine a long straight wire, and we know magnetic fields make circles around long straight wires, and so your Amperian loop obeys that symmetry, so that your magnetic field is constant as you walk around your Amperian loop, okay? All right, so remembering all that stuff. Now, your enclosed current could also be written in this way. It's the integral of the current density with respect to the area, okay? And so that means that you can write the integral of b dot ds is equal to mu naught times the integral of j dot dA. Now remember, you're integrating the current density over the area enclosed by that Amperian loop. All right, now we're going to remember our calculus 3, and calculus 3 tells us Stokes' theorem. And Stokes' theorem says that if you're doing the integral about a closed loop of b dot ds, then, actually not just b, for any vector, you would have the integral of del cross b, or the curl of b, dot dA. Okay? Remember that del is your differential operator, which is partial with respect to x in the x hat direction, plus partial with respect to y in the y hat direction, plus partial with respect to z in the z hat direction. Okay? So it's that differential operator. And the curl is when you do the cross product of your differential operator with whatever vector field you're interested in. In this case, it's the magnetic field. Okay, so applying Stokes' theorem, we can say that it's the integral of del cross b dot dA. And then we already said that this was equal to mu naught times the integral of j dot dA. All right? So since we're integrating over the same area for both the curl of b and the current density, then we can set the arguments of those integrals equal to one another. And that gives us the differential form of Ampere's law, which is that del cross b is equal to mu naught j, where b is the magnetic field and j is your current density. Now in this form, Ampere's law tells us that magnetic fields are caused by currents or current densities, right? But remember, our displacement current told us that a changing electric field can also cause a magnetic field. So that displacement current will break out in a second, but right now let's just call it the displacement current, okay? So if we wanted to add this in to the existing Ampere's law, then we could just do it this way. The integral about the closed loop of b dot ds is equal to mu naught times quantity I enclosed plus I displacement, where I is the enclosed current and ID is the displacement current. So we could just write it that way, and that would be pretty straightforward. If we did that, then that would be equal to mu naught times the integral of the current density j plus the displacement current density j sub d dot dA. Okay? Now we would apply Stokes' theorem just like we did before, so that we end up with the integral of the curl of b dot dA is equal to mu naught times the integral of j plus j sub d dot dA. Then we would set the arguments of those integrals equal to one another, and we would end up with the differential form of Ampere's law, which is that the curl of b is equal to mu naught times j plus j sub d. So it's mu naught times the current density plus the displacement current density. Now let's remember what the displacement current is, and therefore we can define our displacement current density. The displacement current we define as epsilon naught times d phi e dt. Remember that phi is the electric flux here, and the electric flux is the dot product of the electric field with the area vector. Assuming those are pointing in the same direction, then that would be E times A. So then we have our displacement current is equal to epsilon naught times d dt of E times A. Now let's assume that that area vector doesn't change with time, okay? So we can pull that out of our derivative. So then we have that our displacement current is equal to epsilon naught times A times dE dt. Great. Now our current density J sub d is our current divided by the area. So if we look at our definition of our displacement current, we can find our displacement current density just by dividing out by that area. If we do that, then we end up with J sub d is equal to epsilon naught times dE dt. Since our electric field depends upon multiple variables, not just time, but also spatial variables, what we should do instead is say that J sub d is equal to epsilon naught times the partial of our electric field vector with respect to time. And that just teases out any explicit dependence that the electric field might have on time. So that's what we're going to do. Now we're going to take that definition of our displacement current density and plug it back into the equation that we had a minute ago. So if we do that, okay, those two equations are summarized up above, we can combine them. Then we end up with the full differential form of Ampere-Maxwell Law, which is that the curl of B, del cross B, is equal to mu naught J plus mu naught times epsilon naught times partial of the electric field with respect to time. In words, what this tells us is that magnetic fields are caused by currents and by changing electric fields. Okay? Electric fields that change in time. Yay, we did it. Now, what Maxwell did that we're going to do in this lecture is to use all of the four equations that describe electricity and magnetism, which I'll summarize in just a second, and derive that light is an electromagnetic wave that propagates at the speed of light, and you showed what that speed of light should be theoretically in a vacuum, 3 times 10 to the 8th meters per second. Okay? Here's a picture of Maxwell. This accomplishment was so important that what they did was that they took all of those equations and now we call them Maxwell's equations in his honor. Yeah? All right, here we go. Here's Maxwell's equations. Let's summarize them in words and acknowledge how awesome they are before we move on. So we have our del dot B is equal to 0, and that is that the divergence of the magnetic field is equal to 0, and that tells us that there's no magnetic monopoles. Pretty cool. We have that del dot E is equal to rho over epsilon naught, or the divergence of the electric field is equal to rho over epsilon naught, where rho is the charge density, okay? Volume charge density. And epsilon naught is, of course, 8.854 times 10 to the minus 12 in SI units. Okay, so what this tells us is that electric fields are caused by charges. Okay. Next, we have the one we just talked about, the Ampere-Maxwell Law. Del cross B is equal to mu naught J plus mu naught times epsilon naught times partial E with respect to T, or magnetic fields are created by currents or electric fields which change in time. And then finally, we have Faraday's law. Del cross E is equal to negative partial B with respect to T. And what this tells us is that in addition to Gauss's law, which told us that electric fields are caused by charges, we also know now that electric fields can be caused by changing magnetic fields. Okay? All right. Now what Maxwell did, one other thing, I ought to add this on. If you take those four equations and combine it with the Lorentz force law, which is that F is equal to QE plus QV cross B, which tells you how electric fields and magnetic fields cause forces on charges. Okay, so if you take those 5 equations, then you know everything that you need to know to solve problems in classical electricity and magnetism. Pretty impressive. All right, what Maxwell did is he took 2 of those 4 fundamental equations, Faraday's law and the Ampere-Maxwell law, and he solved them simultaneously for the free space condition. The free space condition is when there's no charges and there's no currents or current densities. Okay, so Q is equal to 0, is equal to I is equal to 0, and so is J. All right, so all of those things. Now let's talk about that for just a second. All right, so what this means is that electric and magnetic fields are real things, okay, and that they can exist independently of the charges and moving charges that created them. That in itself is a pretty amazing fundamental thing. You're saying that fields can exist in empty space all by themselves. Neat. Okay, so if you also think about it, what Maxwell did was he showed that light was an oscillating, self-propagating, transverse electromagnetic field, and that field traveled at the speed of light, 3 × 10⁸ meters per second, and he showed that speed came from fundamental constants. So let's do it. No further ado. Okay, here we go. One of the assumptions that we're going to make is something that Maxwell didn't know at the time. This had been proven. Light was a wave. Okay, this had been shown in several experiments. It diffracted, it refracted. Okay, so light's a wave, and it's a transverse wave. So here, transverse means that the direction of oscillation is perpendicular to the direction of propagation. So it oscillates in one direction and moves in another. All right, so let's go with this. We're going to assume that the electric field is oscillating in the y direction, and that the wave itself propagates in the x direction. Now, if you need a refresher on the equations for waves, you should watch another one of my videos, and I'll provide the link, okay? So if you need a refresher on waves, make sure you see that. But I'm going to assume that you understand this equation, okay? So here's the electric field that we're going to assume that our light wave has. Now, we're just assuming this one. You can also prove it's true for other polarizations of the electric field vector. In other words, I've shown here that the electric field is oscillating in just the y direction here. Okay, that's a plane polarized wave, and it's polarized in the y direction. But you can also show that it's polarized in the x direction, or that it's circularly polarized, which means that it would oscillate and the direction of oscillation would change in time. Okay, so you can also show that Maxwell's equations show the same thing for different polarizations of waves. Okay, and for superpositions of waves. They don't have to be this cute little sine function that I have here. Okay, if you use the idea of Fourier transforms, in fact, you can show that any superposition of oscillating waves would work. So you can have wave packets that have funny shapes. It doesn't matter. But we're going to go with the simplest thing because it's the easiest to see. Okay? Let's get going. We're going to start with this electric field. And this electric field is E is equal to E naught times the sine of kx minus omega t in the y hat direction. Now you might be saying that equation isn't kx minus omega t. Yes, it is. Remember, k is your wave number. K is equal to 2 pi over lambda, where lambda is your wavelength. And that's the distance between neighboring crests, or neighboring troughs if you like, okay, one full period of the wave. So that's the wavelength. And then omega is the angular frequency, which is 2 pi f, where f is the frequency of oscillation in hertz. So that gives you the number of times that the wave oscillates in a second. Okay, so let's go. Here's our electric field. Now what we're going to do is we're going to take Faraday's law and we're going to take the Ampere-Maxwell law, and we're going to solve them simultaneously for our electric field that we just defined. Okay? All right, let's start off. Let's see, it looks like I start off with del cross E is equal to minus partial B with respect to t. So I start off with Faraday's law. Okay? I take my electric field vector that we've already got, E is equal to E naught times sine of kx minus omega t in the y hat direction, and I take the curl of that electric field. All right? So when you take the curl of something, what you're doing is you can take the determinant of the 3 by 3 matrix, right? And the first row of your 3 by 3 matrix is your unit vectors. The second row of your 3 by 3 matrix is your del operator, which is, of course, partial with respect to x hat plus partial with respect to y hat plus partial with respect to z hat. Okay, so that's your second row. You take the components of that vector. And in your third row, we have our electric field vector. Now, the x and the y components of that electric field are 0. So you can see that on the third row, the first and the third column are 0. and the only non-zero component is the y component, and so that's going to be E naught times sine of kx minus omega t. Now this E naught is a constant, so I pulled it outside of my determinant, multiplied everything through by E naught. All right? Now the way that you take a determinant of a 3x3 matrix, remember, this should be a refresher. If it's not, you need to go back and look that up. But remember that briefly, the way that you do it is you cross out the column and the top row, and then you take the determinant of the 2x2 matrix that remains. So here we go. That gives us E naught, and if you want the x hat component, that's going to be crossing out the first column in the top row, and then it leaves you with this little 2x2 matrix right here. And then you take the determinant of that 2x2 matrix. So for that, you end up with x hat times partial with respect to y of 0 minus partial with respect to z of sine kx minus omega t. Okay? Now, partial with respect to y of 0 is, of course, 0. So that leaves us with x hat times minus partial with respect to z of sine kx minus omega t. Okay, now the y hat component. You're crossing out the second column in the top row, and now you take the determinant of that little 2x2 matrix. Well, there you have partial with respect to x of 0 minus partial with respect to z of 0. So that gives you 0 trivially. Okay, finally, the z hat component. You cross out the third column in the top row, and you take the determinant of that little 2x2 matrix. So we have plus z hat times partial with respect to x is sine kx minus omega t minus partial with respect to y of 0. Of course, that's 0, so you just end up for the z hat component with partial with respect to x of sine kx minus omega t. All right, now let's go through and look at these partials. The partial with respect to z of sine kx minus omega t is 0 because there's no explicit z dependence in that. So that means that the x hat and the y hat terms are both 0, and we're just left with the z hat term. So now we take the partial with respect to x of sine kx minus omega t. That gives us, all right, when we go through the whole thing, remember we're multiplying everything times E naught. That gives us E naught times k times cosine kx minus omega t in the z hat direction. So that's our gradient, our curl. Okay, so that's our curl, and then remember its curl of E is equal to minus partial b with respect to t. So we've done the curl of E part. Now we can solve for b using this little differential equation. So if we want to do that, then we multiply by dt on both sides and we integrate. So we end up with b is equal to the negative integral of dt times E naught k cosine kx minus omega t in the z hat direction. When we integrate a cosine, we get a sine, okay? So when we do that integration, we're going to get minus E naught k over omega, right, over minus omega times sine of kx minus omega t, and then plus some additive constant, right, in the z hat direction. Now we can set this constant equal to 0. In other words, we don't really care if we have some background b field that adds on to everything. It doesn't matter because we're taking a lot of derivatives anyway, and it's only the rate of change of b that would matter. So if there's some additive constant, it's unimportant. So let's just set that equal to 0, okay? So the minus signs cancel out, and we end up with b is equal to k over omega times E naught sine kx minus omega t in the z hat. Now let's remember what omega and k are. K is our wave number, 2 pi over lambda, and omega is our angular frequency, 2 pi f. So if we plug in for those two things, we get out front 2 pi over lambda over 2 pi f, right? Okay, so what that means, our 2 pi's are going to cancel out, and then out front here we just have 1 over lambda f, okay? Now lambda f is defined as the speed of a wave. You're multiplying the wavelength times the frequency, and that gives you a speed. If you need a refresher on that, make sure to look that up, okay? It's all in the stuff on waves. So v is equal to lambda f by definition. And so that means that our magnetic field B is equal to E naught over v, which is the speed, times sine kx minus omega t in the z hat direction. Okay? So we started off with our electric field, and we arrived at an equation for our magnetic field. You can see that the magnetic field direction is perpendicular to the direction of the electric field oscillation. The electric field oscillated in the y-hat direction, and the magnetic field oscillated in the z-hat direction. However, you can see they both propagate in x, so they're both moving in x. Okay? All right. Now we're going to take this equation for the magnetic field, and we're going to use our other equation, right, which is the Ampere-Maxwell Law. Right? We're going to use that equation, and we're going to solve. So here we go. Remember the Ampere-Maxwell Law in the case where there's no currents is del cross B is equal to mu naught epsilon naught times partial E with respect to t. Okay? Now we started off with an electric field vector that was E naught times sine kx minus omega t in the y-hat direction. The right-hand side of our Ampere-Maxwell Law contains the partial E with respect to t. So if we take the partial of that electric field vector with respect to time, then I end up with minus omega E naught cosine kx minus omega t in the y-hat direction. Okay, so that's our partial. Now we also have to solve for the curl of B on the left-hand side of that equation. I'm not going to belabor the point too much about how to take a curl, okay? So I'll just tell you, all right? I saved a little space by using BZ. I saved a little space here. And so what I end up with for my curl of B is going to be x hat times partial of BZ with respect to y minus y hat partial of BZ with respect to x. Okay, the z component is 0. Now, if you take the partial with respect to y of BZ, you get 0 because there's no explicit dependence in B on the y variable. Okay, so that partial is 0, which means that the only component that survives is the y hat component. So if you look at your y hat component, you've got your partial of BZ with respect to x. So when you take that partial derivative, you end up with E naught k over V times cosine of kx minus omega t. Okay? Remember that your component there was E naught over V times sine kx minus omega t. So when you take the partial of BZ with respect to x, this is what you end up with. Okay? So there's our curl. Okay? The curl of B is minus E naught k over V cosine of kx minus omega t in the y-hat direction. So we're going to couple that with the partial of E with respect to t that we solved for earlier. Okay? And we're going to plug in to the Ampere-Maxwell equation. And we end up with minus mu naught epsilon naught omega E naught cosine kx minus omega t y hat equals minus E naught k over V cosine kx minus omega t in the y hat. So they're both in the y hat, yay, phew, right? The cosines are going to cancel out on both sides. The E naughts are going to cancel out on both sides. And what we're left with that doesn't cancel is the following. Mu naught epsilon naught omega equals k over V. Okay? So now the whole goal of this was to solve for the speed V. So let's keep going here. Let's solve for V. If I solve this symbol equation for V, I end up with V is equal to k over omega times 1 over mu naught epsilon naught. Now, yet again, k is 2 pi over lambda, and omega is 2 pi f. So plugging in for those things, I end up with V is equal to 2 pi over lambda times 2 pi f. 2 pi f is in the bottom. And then that's times 1 over mu naught epsilon naught. All right. Well, the 2 pi's cancel out, and I'm left with 1 over lambda f times 1 over mu naught epsilon naught. Yet again, lambda f is V. So 1 over V is equal to 1 over V times 1 over mu naught epsilon naught. Now multiplying through by V on both sides, I end up with V squared is equal to 1 over mu naught epsilon naught. So that must mean that the speed of that wave, our electromagnetic wave, is equal to 1 over the square root of mu naught epsilon naught. All right? Now, mu naught is 4 pi times 10 to the minus 7 in SI units. Epsilon naught is 8.854 times 10 to the minus 12 in SI units. So if I plug in those numbers into that equation, I end up with 3 times 10 to the 8th meters per second. Pretty cool, right? That's the known speed of light in a vacuum. Phew. So what did we just do? Well, we showed that an electric field that is a transverse wave, in other words, the direction of oscillation is perpendicular to the direction of propagation. That oscillating electric field will induce a magnetic field. Okay? Well, it keeps going. That's why it's called a self-propagating thing, right? The electric field oscillates, which leads to a magnetic field. The magnetic field oscillates, which leads to an electric field. So that's how electric and magnetic fields can keep existing even in the absence of a charge. Okay? They can keep existing even without the charge, because as they propagate, they're still oscillating. If they're oscillating, then they're changing in time, and an oscillating electric field induces a magnetic field, but an oscillating magnetic field induces an electric field, and so it just keeps going. We also showed, right, the speed at which this happens. And that speed is related to some fundamental constants that we already knew about from electricity and magnetism, the permeability of free space and the permittivity of free space. So we showed that the speed of light comes from those fundamental constants, which makes it a fundamental constant. Okay? So here's a picture of what we're looking at. Here the electric field is pictured in blue, and the magnetic field is pictured in red. One wavelength is shown, just for scale there. And you can see that the electric field is oscillating in one direction, which is perpendicular to the magnetic field, but both of those directions are perpendicular to the direction of propagation, which is shown here by an arrow. Right? Now, yet again, we showed this for one polarization of the electric field vector, but other polarizations will work too, and you can prove it. Okay? All right. I hope that that was at least somewhat mind-blowing. You might have known all those fundamental facts before, but seeing them derived should definitely pack a punch. Okay? If you have any questions, let me know, and I'll see you around.